Okay, so this is the outline of chapter 28. So first I will introduce magnetic field, the B field. Actually, if you call it magnetic field, it is not that correct, but at least in this textbook, it mentioned the B field is the magnetic field. So I just follow that. I just mentioned that if you need to be more rigorous, B field has another name rather than magnetic field, but I just follow the textbook, what the textbook write, and later on I just keep doing calling the B field as a magnetic field, or sometimes I just call B field to be B field. Okay, so next I will introduce the cross field means if we have E field and B field perpendicular to each other, we call cross fields. So within the cross fields, there are some interesting phenomena. Okay, including discovery of electron with the Hall effect. Okay, so and then in the cross field, not really cross field. I think if you have a charge entering the B field, then it can have a circular motion. If it can have a circular motion, yeah, because there will be a force acting on the charge. Okay, and then this force will keep changing the direction and then make the charge have a circular motion. Okay, and then we will talk about the cyclotron and synchrotron, two types of particle accelerator. Okay, particle accelerator, 粒子加速器, and then we'll talk about a magnetic force on a current carrying wire. Okay, so which is somehow the extension of here. So here we will talk about the so-called the Lorentz force, 洛伦智力, Lorentz force, and then this is also a kind of a Lorentz force, I think. And then we'll talk about the torque on a current loop, and then the magnetic dipole moment. So before we have learned something called electric dipole moment. So here we have the couple. So we call it So for E field we call it electric dipole moment or electric dipole. Here we call it magnetic dipole or magnetic dipole moment. Okay, so here we have the definition of the magnetic field or B field. Actually, just like what I've mentioned, if you need a rigorous name, it should be called magnetic flux density. Magnetic flux density rather than magnetic field. Magnetic field should be something like H field. But in this textbook we never use this variable, so it's fine to call B field to be magnetic field, but they are a little bit different. At least the SI unit are different from each other. Okay, so B and H should have a relationship like I think should be like H field to be B field divided by mu naught, something like that. Hope I remember correctly. It should be divided by mu naught or so the SI unit is different. Okay, we'll talk about this so-called the permeability constant, which is a couple of the permeability constant, permittivity constant. Okay, so this is called magnetic flux density, rigorously. In Chinese, it is called 磁通量密度。磁通量密度。Okay, so actually, for the E field, you know what is an electric flux. When we learn Gauss law, you know what is electric flux. Electric flux is like phi E to be integration of E dot dA. Is so-called electric flux across a surface. Okay, so if we change this one to be B field, then it will be like that. Okay, so so this is so-called this is the electric flux. So if we divide it by the area, so this would be like phi B to be integration, not necessarily closed surface, B dot dA. Okay, so this one will be magnetic flux, and this one should be like the magnetic flux density. Okay, yeah, so yeah, this is the rigorous name, but later on we will keep using magnetic field, or I just call it B field. So here B field can be defined as a vector quantity that exists when it exerts a force Fb on a charge moving with velocity v. Okay, so yeah, we have this expression. So this is like a definition. So if you have a uniform B field in the space, and then there is a charged particle moving in this uniform B field, there will be a force acting on the charged particle. Okay, and then if we have this force divided by the charge amount of this of the charge, and then divided by the velocity, okay, we assume that yeah, this is the uniform speed of the moving charge particle. Okay, so if we have Fb divided by Q divided by V, it should be a constant. This constant is called B, which is actually the B field. Okay, of course it's only a magnitude. Then we need to talk about the direction, because it is a vector. B field is a vector. It's a vector quantity. So this is the magnitude, and when we talk about the direction, we should have this expression. So this expression, this one is not a multiplication, this one is a cross product. This one is a cross product. Yeah, here. The cross product of this velocity and the B field. So I think you should have learned the cross product in high school physics, but actually I will also explain what it really is. Okay, so yeah, so this is so-called the Lorentz force. The Lorentz force. This Fb is called Lorentz force. Or in some of the material, they will say the general Lorentz force should be like the general Lorentz force should be like Fb to be QE plus V cross B, something like that. This will be the general case. Yeah, because rigorously when we consider the relativistic effect, yeah, E field and B field are the same thing. They are so-called the E-B field tensor. So in 4 dimensions. So yeah, we can't really distinguish them. I think in 6 dimension. Yeah, so in different reference frame, the E field can convert to B field, the B field can convert to E field. So, but that's maybe too complicated for you. So here, you need to be careful that here when we talk about this Lorentz force, yeah, so the velocity and the B field all measured in the same reference frame. Because in different inertial reference frame, the velocity may be different, and then you will see, oh, if your reference frame is moving with the particle, then you feel like the particle doesn't really moving, but actually you need to consider the B field, yeah, doesn't move, and then you are at that reference frame, and then you see how fast is the particle is moving. Okay, so here in this equation, we have Fb to be the Lorentz force to equals Q. Q is the charge amount, and then V is the velocity cross with the B field. Okay, so we have the cross product. And if we only consider the magnitude, okay, for this cross product, it will be like the magnitude of the first vector and the magnitude of the second vector to be V times B, and then also take the absolute value of Q, and then for the cross product we also need to multiply by sine of theta. Okay, sine of theta, not theta, this would be phi. Okay, so phi is the angle between the direction of the velocity v and the magnetic field b. Okay, so this phi is the angle between these two vectors. Okay. Yeah. So here we need to mention, how do we determine the direction of this? Yeah, this is not that trivial then as the electrical force. For the electrical force, Fe equals Q times E, which means that if Q is positive, Fe and E points to the same direction. If Q is negative, Fe and E points to the opposite direction. So yeah, it's easy to determine the direction of the force. But here, yeah, actually this 1, 2, 3 vector points to different direction. Okay, so we need to be so we need to know how we can determine the direction of them. At least we know these two. Then how do we determine the direction of FB? Okay, which means how do we determine the direction of a cross product? Okay, so yeah, so here if we consider V is pointing to that direction, B is pointing to another direction. So we need to use the right hand rule. So we keep using right hand rule. Okay, throughout this semester, we will not use left hand rule. So don't try to use left hand rule sometimes. Yeah, of course you can use left hand rule all the way, but all the equation will have a negative sign. Okay, it makes everything the reverse direction, because if you have right hand rule, it will be something like this. So V cross B to be this direction, but if you have left hand rule, it will be like this: V cross B to point to the opposite direction. Yeah, so let's see. So keep in mind, we need to use right hand all the way. So in this case, if V points to this direction, B points to this direction, then you use your forefinger points to the direction of the first vector, which means V, because we are calculating V cross B. Okay, so we are calculating V cross B. We use the forefinger pointing to V, and then you swing it to the vector B. Okay, like this, V cross B. Okay, and then your thumb will point to the direction of V cross B. Okay, so that's simple. Okay, so this is the first step. Point to the direction of V, and then cross to B, and then your thumb, and then here your thumb will point to the direction of V cross B. Okay, like this. And then if Q is positive, then FB points to this direction. And if Q is negative, then FB points to the opposite direction. Okay, for this case, Q is negative. Okay, for this case, Q is negative. And if for this case, Q is positive. Okay, Q is positive. So FB points to the same direction of V cross B. And then if this one Q is negative, FV points to the opposite direction of V cross B. Okay, so that like that. And keep in mind that the angle phi we define is like the phi should be larger than or equal to 0 and less than or equal to 180 degree. Okay, so keep this in mind. Don't try to make phi to be 270 degree. You can say, oh, I try to make it like this and then rotate for 270 degree. So my thumb point to the opposite direction. But yeah, so just keep in mind that phi should be between 0 and 180 degree. Don't try to twist your hand like this. Okay, so yeah, so here we know that FB should be perpendicular to both V and B. Okay, FB perpendicular to V, FB perpendicular to B. Okay, you can see like this, Okay, that is V points to that direction. we consider direction. Okay, so this is a right angle. This is also a right angle. Okay. Yeah. Pretty much like this. So let me try to remind you some of the characteristic of the cross product and also the dot product. Okay, so this is the cross product. If we have V cross B and then take the absolute value, which is like take the magnitude of this vector, which is like V times B times sine of phi. Phi is the angle between them. So if we have V to be like this, and then if we have a B like this, okay, so actually the magnitude of this is like this. Okay, so first of all, we know yeah, the direction. For the direction, okay, we can use the right hand rule. Okay, use V, use your forefinger point to the direction of V and then cross to B, and then your thumb will pointing upwards. Okay, so this is V cross B. Okay, here we don't consider Q. Okay, if Q is positive or Q, FB also pointing upward. Okay, but I just mentioned the cross product only here. Okay, so this is the direction of the cross product, and actually V times B times sine of theta is actually the area of this parallelogram. Okay, 这个平行四边形的面积。Okay, so this is actually V cross B. Take the absolute value. Okay, because you know when you have a triangle, okay, if you know this is A, this is B, this is let's say this is phi. Okay, the area of this triangle is 1/2 AB sine of phi. Okay, so this is one of the triangle. This is another one. So you multiply by 2. So this is like V times B times sine of phi, and then this is actually phi. Or maybe I just make it like this is phi. This is phi. So this is the geometry meaning of the cross product. And for the dot product, okay, just remind you a bit. If we have a dot product, A dot B, okay, it will be like A times B times cosine of theta. Okay, so here we also have the multiplication of the two magnitude of the vector, and then for the cross product we have sine of phi. For the dot product we have cosine of theta. So here if we have this is A and then this is B, it will be like you just project this one onto the project B onto vector A, or the vice versa. You can also project this one there. But actually this one, if you project B onto A, this segment will be like B. This is theta. Okay, so this line will be B times cosine of theta. Okay, so this is like the vector. Okay, the vector, the magnitude of A times the projection of B onto A. Okay, so that like this. Okay, but for dot product, we can have A dot B equal B dot A. Okay, these two are the same, but for this one, V cross B and then B cross A, like V cross B and B cross V will have a negative sign. So don't try to swap the order of the cross product freely. Yeah. You need to care about the minus sign here. Okay, if B and V are pointing to the same direction or opposite direction, then the cross product will be a zero vector. Yeah. So just some special case for the cross product. Okay, so next here, so this is nothing special. So it says the force FB acting on a charged particle moving with velocity v through a magnetic field B is always perpendicular to V and B, just as what I've mentioned. Okay, so here we have a quick checkpoint. We see this, the figure shows three situations in which a charged particle with velocity v travel through a uniform magnetic field B. In each situation, what is the direction of the magnetic force Fb on the particle? Okay, so try to practice a bit about how to determine the direction of the cross product and also the Lorentz force. Okay, so for this one, okay, we have a positive charge and then V points to the negative x-axis. Okay, so this is x-axis, this is y-axis, and then this is z-axis. Okay, so V points to the negative x-axis, and then B points to the negative y-axis. Okay, so what is the direction of FB? Z direction, Z direction, yeah, right. So this is a z-axis, positive z-axis, positive z-axis. Okay, which means this one. This is FB. Okay, and then for the second one, this is a negative charge, V cross B. V cross B should be point to the right side, and then this is a negative charge, so it will point to the left side. Okay, so this is FB. FB. And yeah, or we can say this is a negative x-axis. Okay, and then here V and B points to opposite direction, so which means that the cross product of them should be 0. Okay, so this is 0, so it has no direction. Okay, so this is easy. Okay, but based on that, I would like to also yeah, so yeah, maybe I can just put the answer here, but yeah, it's fine. Okay, so based on this, I also want to supplement some of the cross product about in the unit vector. Yeah, I mean in terms of the unit vector, which means that before we sometimes use I hat, J hat, K hat to stand for the unit vector in x-axis, y-axis, and z-axis. If we also use the unit vector notation to explain the cross product, then there will be some, yeah, there is another way to calculate this kind of stuff. Okay, so let's see. Yeah, so for I cross, let's say if we have a cross B, A cross B, so we may have or maybe I just, because yeah, in this case, yes, so let me just write it like this. I just don't, sorry, maybe I just draw it like this. Okay, with 9, 3 times 3. Okay, so so we can have I cross I, and then I cross J, and then I cross K, and then J cross I, and then J cross J, and then J cross K, and then K cross I, K cross J, and then K cross K. Okay, like this. We have totally 9 combination, because for both operands it can be either I, J, and K. Of course, in general case, it can be a vector like B equals Bx times I, and then By plus J, and then Bz times K hat, something like that, and then you need to use the distribution. And then, for example, if B is like this, V is also like a Vxi hat, and then Vyj hat, and then Vzk hat. And then if you have a v cross b, then you need to distribute to have totally like terms, like what you have done for the algebra, like yeah, I suppose you know. Okay, so here let's see what are the result of them. So first of all, we have I cross I, J cross J, K cross K. As I mentioned, if they are parallel to each other, it should be a zero vector. Zero vector. It should be a zero vector. So this is easy. Okay, so if we have I cross J, it should be K hat. If we have I cross K hat, it should be negative J hat. If we have J cross I hat, it should be negative K hat. If we have J cross K, it should be I hat. And then if we have K cross I, it should be J hat. If we have K cross J, it should be negative I hat. Okay, so how to remember? How to remember? Okay, so it is like this one, and this one is positive, and then this one, and this one is negative. Okay, so still not so trivial. But actually, you can see. I will let you remember like this, or at least I will remember like this. If we have I, J, K hat, draw it like this. So if we have the direction in clockwise, like this, like this, like this, it will be positive. What does it mean? If we have I cross J, it becomes K hat. If we have J cross cross K, we have I hat. If we have K cross I, we have J hat, all the way positive, which means this one, and also this one. So it is like in order. I, J, K complex to I, and then J complex to I, K, I, J. So in the forward direction. Okay. If it is in opposite, reverse direction, like this, counterclockwise direction, so it should be a negative sign, which means that if we have I cross K, it will be negative J. I cross K to be negative J, which is this one, and then K cross J will be negative I. K cross J to be negative this one, and then if we have J cross I will be negative K. J cross I to be negative K. These three cases. Okay, so I'll use this one to let you remember how, or you can just try to count I, J in order, so it should be positive, and then I, K is reverse order. Okay, you consider I, J, K, I, J, I, J, K. Okay, look forever. So if it is like this, it is in order, and then if it is like this, it is reverse order. Okay, so keep in mind like this, and then you can also know that, okay, for the XYZ, it is also following this one, which means that X cross to Y, and then your thumb will point to the C direction, which is like X cross Y point to the C direction. Of course, C is like this, but yeah, if you draw it in 3D, C is somehow like that in a 45-degree angle. Okay, so yeah, so in that case, this XYZ axis also follow the axis also follow the right hand rule. Okay, like this. Okay, so if we use the univector notation to come up with this question, we don't need to use the right hand rule anymore, which is like this one. V should be like negative V and then times I hat. Okay, this is negative x-axis, so we just make it V to be a positive value, and then multiply by a negative I hat, so that V points to the negative x-axis. And then here B points to the negative y-axis, so it is like negative B and then J hat, like this. So in that case, FB is actually Q Q is a positive value, so we just make it Q. And then V cross B. V cross B will be like negative V I hat, and then cross negative B J hat, like this. So we have QVB to be positive value, and then we have this negative sign and this negative sign, so it turns out to be plus QVB. Okay, all of them are positive value, and then we have I cross J. I cross J is in order, so it should be K. Okay, so it is in positive Z direction. Okay, and also for this one, V is this one, negative y-axis. Okay, so V equals negative V, and then negative y-axis is negative J hat. Okay, and then for B is in the negative Z-axis. B is in negative Z-axis. So B and then K hat. Okay, and this one is a negative charge. So FB is like a negative Q, and then V is a negative V J hat, and then cross with negative B and then K hat. Okay, so we altogether have a 3 minus sign, I should say 3 minus sign, so we have negative QVB, and then we have J cross K, I, J, K, I, so it should be positive I hat, so in this case it points to the negative x-axis. And then for C, it is like, this is like J hat, and then this is negative J hat, of course times V, this is times B. Okay, so J hat cross J hat will be 0 vector. Okay, so this one FB equals 0 vector. Okay, so this is the unit vector notation. So for some of the selected problem, there may be that may require you to express the answer using the unit vector notation, and actually it will be useful for you later on, even though you are not working on the electromagnetics. Maybe it will be useful for other mechanical problems. Okay, so here we also talk about the magnetic field line. So which is similar to the electric field line. So it also has a characteristic line, the direction of the tangent to the magnetic field line at any point gives the direction of the B at that point. Okay, and then the space of the line represents the magnitude of B. So the magnetic field is stronger where the lines are closer together and conversely. Okay, so it is actually the same as the electric field line. So you just change the E field to B field, and then it is from the electric field line to the magnetic field line. So yeah, nearly the same things. Okay, so this is like if you have a magnetic bar here, and then you place some iron fillings. So the irons can be attracted by the magnetic bar. So yeah, so these iron fillings will follow the magnetic field lines. Okay, just like that. Okay, so here we also mentioned that for the magnetic bar, just as what we have learned in primary class, you will know that for magnetic bar we always have two poles. Okay, two poles. Okay, so it says the closed field lines enter one end of magnet and exceed the other end. Okay, which is like, okay, it start from this side, and then you go, of course this is like starting from the middle and then go to this side and then coming back. Okay, or you can consider it is start from here and then end it here, but of course there are something inside, so yeah, maybe not that good, but at least it is like it start from the North Pole and then end at the South Pole, always like that. similar to the electric field line. For the electric field line, it always start from the electric field line always start from the positive charge and then end at the negative charge. For a dipole, it will be like that, like an apple shape, something like that. If you remember, okay. So it for a electric field line, yeah. And actually, this is an electric dipole. Later on, we also have the magnetic dipole. So yeah, actually, this shape is the same as this one. It's actually the same as this one. Just turn it 90 degree. Okay, so at least and I mean, when we are in primary class, we know that even though we cut the magnet bar in two pieces, it turns out to be, oh, this is North Pole, this is South Pole, this is North Pole, this is South Pole. Okay, you cannot really separate a single North Pole or single South Pole to appear independently. It is not possible to do that. At least till now, it is like that. Okay, so it says opposite magnetic pole attract each other. Okay, so 异性相吸嘛。Okay, and like magnetic poles repel each other， 就同性相斥，所以就是 okay. So that is what we learn in primary school. You already know that. But here I would like to mention that actually the magnetic monopole does not exist. Okay, in Chinese this is called 磁单极. Okay, it does not really exist. It doesn't like the charge. For the charge, you can have a single positive charge. You can have a single negative charge to appear independently. But for the magnetic pole, it does not. The magnetic monopole does not really exist. Even if you try to separate the magnetic dipole in two parts, then it turns out to be two magnetic dipole, and then you further divide it into smaller and smaller, and then it is still a magnetic dipole. Okay, so if you're interested, you can check it on the Wikipedia. So it says magnetism in the magnet bar and the electromagnet magnets is not caused by magnetic monopoles, and indeed there is no experiment or experimental evidence that magnetic monopole exists. Okay, so later on in chapter 32 we will learn about the Maxwell equation. So that Maxwell equation will base on the fact that we only have a magnetic dipole, we can't have a magnetic monopole. So in that case, for the Gauss law, in chapter 23, you know the Gauss law is like epsilon naught integration of E dot dA to be Q enclosed. So this is for the E field, but for the B field, it has a version like integration of B dot dA to be 0. Yeah, because it is always monopole. So if you just draw a Gaussian surface, inside it must be 0 because the positive and negative with the same amount always exist together. So you can never separate a single magnetic monopole. So that the right side will be a 0. But of course, the scientists also imagine if there exists a magnetic monopole, or what will the Maxwell equation be, and that's another story. But yeah, we will not go deep into that here. Okay, so anyway.